This is a really lovely sequences problem from this year's IMO. The setup is so simple. AN is equal to the number of times AN minus 1 has appeared in the list so far. So you just count how many times each term has appeared in the list. That count becomes the next term in the sequence. But this is problem 3, so it's the final problem on day 1 and the most challenging. Looking at the statistics, we can see that the vast majority of competitors scored 0 on this problem, and only a handful were able to score more than 4 out of 7. We need to prove that every second term in the sequence is eventually periodic, meaning that the same subsequence is going to repeat forever. I had a lot of fun thinking about this problem, so I hope you will enjoy this video explanation. So to get started with the sequence, we're just going to play around, try some examples and see what happens. Let's start with a case where n is equal to 1, so there's one term initially in the sequence, and it can be anything, so let's just start with the number 3. Okay, so the 3 has appeared once, so the next number to appear is 1. The 1 has appeared once, so again we place a 1. Now 1 has appeared twice, so we place a 2. 2 has appeared once, we place a 1. 1 has now appeared 3 times, we place a 3. We keep going, and after some time we notice that we do get every second term repeating in the cycle 1, 2, 3, 1, 2, 3, 1, 2, 3. And that is what we need to prove, is that every second term forms this sequence which is eventually periodic. So it'll form a sequence which repeats itself again and again. So let's just try another example, see what happens. Again, n is equal to 1. We'll start with one term, which is a 5. 5 has appeared once, we place a 1. 1 has appeared once, we place a 1. 1 has appeared twice, we place a 2. Again, we keep going. And it takes a bit longer this time to get that repeating subsequence. But eventually we do get there. It's 1, 2, 3, 4, 5. Let's try an example. We start with a 2-term sequence, say 2 different integers 3 and 5. And this time the repeating subsequence is 2, 3, 1, 4, 5, or 3, 1, 4, 5, 2, or 1, 4, 5, 2, 3. Anything in that order, it's periodic, so it doesn't matter where we start. Those 5 terms keep on repeating in that same order. Alright, so from those examples, you may have already made some observations yourself about how these sequences behave. And here are some of the observations I made by looking at these examples and several others. Number 1, when a new number appears for the first time in a sequence, the next term must be 1. Okay, because the number has appeared once, we then must place a 1. Second, eventually a new number must appear in the sequence, so a 1 must eventually appear in the sequence. Once the 1 does appear, the next term must increase by 1 every time. So if the last time a 1 occurred, it was followed by a 7, the next time a 1 occurs, it must be followed by an 8, then a 9, and so on. And similarly for all other numbers. So if any number x appears followed by a y, the next time x appears, it must be followed by y plus 1. Just because the count of each number increments by 1 every time. So not only must the 1 appear, but it must appear infinitely often, because each time it does appear, its count is going to increase by 1. So eventually this must add a new number to the sequence, which then introduces another 1. And the last observation I've made here, which from these examples that I've shown so far, is that the repeating subsequence appears to always be a permutation of 1, 2, 3 to n, where n is the maximum of the initial sequence. This was certainly true for the 3 examples I've shown so far, and when I looked at more examples myself, it did appear that this was always happening. However, that conjecture was actually false. And here's an example. If we start with this initial sequence, what happens is we get a repeating subsequence, which is just 1, 2, 1, 2, 1, 2. Okay, not 1, 2, 3 all the way to 7. So looking at examples is good, looking at examples is great, I love examples. But of course we do need to understand the sequence and then also make a proof and prove that we always get this repeating subsequence. So in all the examples we've seen so far, including that last one, the subsequence that repeated was a permutation of 1, 2 to n. Although n did not have to be equal to the maximum of the sequence, it was less than or equal. Now why does that have to be the case? In order to answer this question, I'm going to show a new way of representing the sequence. I'm going to use an xy plane where the x-axis represents the number and the y-axis represents the count. So a bit like a histogram, but I'm actually going to write the numbers in the plane, so in the bar where the histogram would be, so kind of like a dot plot with numbers. I'm just going to call it a histogram representation. So the idea with this is we're going to put a 0 for each term in the initial sequence, and then place each term an with an x value of the next term an plus 1. And we'll stack it on top of any other numbers that are already there so that the y value will actually give the count, just like a histogram. Okay, so it might look a little bit confusing, but it's actually very, very useful. To explain it a little bit more clearly, if we take an example with the initial sequence 3, 5, we put a 0 above 3 and a 0 above 5. Then the 5 has a count of 1, so we place a 5 above 1. Then 1 has a count of 1, so we place a 1 above the existing 1, which gives 1 a count of 2. So once we understand this histogram representation, we can use it to show why the repeating subsequence must be a permutation of 1, 2, ... to n, where n has to be less than or equal to the maximum of the initial sequence. So to start with, why does n have to be less than that maximum? So if we look at this example where we started from the sequence 3, 5, and think about why can't 6 reach a count of 6 in this sequence? So as 6 did not appear in the initial sequence, the only way it can appear is as the count of another number. But even if each of the numbers 1, 2, 3, 4, 5 all reach a count of 6, that only gives 6 a count of 5. So there's no way 6 can reach a count of 6, and similarly 7 cannot reach a count of 6, and in general that's going to be true for any number that's larger than the maximum of the original sequence. So in general, if we say m is the initial maximum of the initial sequence, in order for any k greater than m to reach a count of k, there would already have to be another j greater than m that has reached a count. But initially we did not have this, so it's not possible for any k greater than m to reach a count of m, so therefore it cannot be part of that infinitely repeating sequence. So that's good. N has to be less than that initial maximum. But why does the repeating subsequence have to be a permutation of 1, 2, 3, ... to n? Why can't it skip a number? Like, why couldn't we have a repeating subsequence of 1, 3, 1, 3, 1, 3, for example? So remember that the repeating subsequence can only contain small numbers. It can't contain large numbers. And once the counts of these small numbers increase beyond a certain point, then a sequence is going to alternate between large, small, large, small, large, small. Not only are the large numbers counts of the small numbers, but the small numbers are also counts of the large numbers, okay? Because that's just the way the sequence is defined. But each large number must appear once before it can appear twice. So similarly, it must appear x times before it can appear x plus 1 times. In this example, it's not possible for 9 to reach a count of 3 before it reaches a count of 2. Clearly that's a contradiction. So with these two observations, that allows us to conclude that any repeating subsequence must be a permutation of 1 to n. For some m which is less than or equal to the maximum, m there is the maximum of the initial sequence we started with. Now we need to prove that those repeating numbers not only repeat, but repeat in the same order over and over again in a periodic way. So in order to prove that, I'm going to use another observation from this histogram diagram, and that is that it appears that each column of numbers, once we get past that maximum, appears to be the same. Okay, we're getting this yellow column, 3, 5, 2, 1, 4, again and again. Now, the order of numbers in that column does not correspond directly to the repeating subsequence. So the repeating subsequence here is actually 2, 3, 1, 4, 5. So it's in a slightly different order to the column. But actually we can show that the position of each number in the column does allow us to get the repeating subsequence. Okay, because the y value of each number in the histogram gives the count of the next term. So if we look at this column, for example, and starting from the bottom, that 3 in the first row means that the sequence must contain 3, 10, 1. The 5 in the second row means the sequence must contain 5, 10, 2. So the 5 must be followed by a 2 as the next small number. And similarly, we can map every small number to the following small number, and that would give us the repeating subsequence 3, 1, 4, 5, 2. So it is actually the case that the order of the numbers in each column does completely determine the repeating subsequence. If we can prove that the order of each column remains the same to infinity, we can prove that we will get a repeating subsequence. So in order to do that, let's define some terms. So let's call any numbers that repeat infinitely repeating numbers, and any numbers that are larger than the initial maximum of the sequence be large numbers. No number can be both repeating and large because, as we saw before, a large number can never reach a large count. We also saw before that there must be at least one repeating number, that is the number 1, because as the counts increase to infinity, a new number would always appear, giving another 1 in the sequence. Alright, so now let's consider the point in the sequence where all repeating numbers have counts that are large numbers. And a new large number, say x, has just been added for the first time. We'll let x be the mth term in the sequence, where m was defined in the question. M is the point after which the sequence is going to become periodic. So as an example, in this sequence here, all the numbers from 1 to 5 have large counts now, counts that are larger than 5. And the number 3 has just been added for the 8th time, giving x equals 8 as the new large number in the sequence. So I'm going to prove that that first repeating number to reach a count of x must also be the first number to reach a count of x plus 1, x plus 2, and all numbers larger than x, which would mean that this repeating number would always continue to be the first number in each column. Similarly, the second number to reach a count of x would always stay in the second position, and so on until the nth position, meaning that the order of numbers in each column must remain the same. So if we say let the first number to reach a count of x be p, and in this example, p was 3 there because 3 was the first to reach a count of x is equal to 8. And let's consider whether another number q could reach a count of x plus 1 before p does. So for example, could the number 5 reach a count of 9 before the number 3 does? So if there were another number, say q, that reached a count of x plus 1 before p did, it would turn out that there would need to be two large numbers that both reached a count of q before p reaches the count of x plus 1, because we're already far enough along the sequence that repeating numbers can only appear as counts of large numbers. So is it possible, for example, for 5 to reach a count of 9 before 3 reaches a count of 9? Or actually no, it's not possible for two large numbers to reach an equal count without a new large number being added between them. And this is going to be a lemma which I will need to prove in order to complete my proof. So if we look at some examples, it always does seem to appear that those large numbers don't reach an equal height until a new large number is added on the end. In order to prove that, just remember that if x appears followed by a y, the next time x appears it must be followed by y plus 1. So in our histogram representation, what that means is if a number is going to appear in one column, it must appear in the column directly to its left. So one thing that this implies is that a large number can't reach a count greater than any of the numbers below it. Okay, so a column can't be higher than any column to the left of it. So that means that if two large numbers were to reach an equal count, it must be the case that two consecutive large numbers reach an equal count. Let's call them y and y plus 1. So if y and y plus 1 were to reach an equal count without a new large number being added between them, then the latest number, say x, to reach a count of y, must also reach a count of y plus 1. Because all numbers in that y plus 1 column must also exist in the left-hand column.
But that's silly. Why is that mouse moving while this mouse is moving?
Yeah, because you're moving it around. In other words, there must have already been two other columns that both reached the same height, that is the height of x, again without a new large number being added between them. So we get that situation where the condition for these two equal height columns to come into existence is that there were already two columns that reach an equal height. But the first large number to be added must have been added with a count of 1. And if another large number were added with a count of 1, then that would be a new large number. So therefore, we can conclude that two large numbers cannot reach an equal count without a new large number being added between them. Now, with that, we can conclude that the first repeating number to reach a count of x must also be the first one to reach a count of x plus 1, x plus 2, and so on, and would always stay in that first position. The same lemma implies actually that the second number to reach a count of x must also be the second one to reach a count of x plus 1 and would always maintain that second position. Again, because if another number were to overtake it, that would require that number appearing twice in the sequence before p reached a count of x plus 2 and a new large number was added.
Oh, Papa, you're so much to do word again.
Continuing in this way, we can conclude that the nth number to reach a count of x must also be the nth number to reach a count of x plus 1 and must retain its position in the column. Once we have that, we can conclude that all numbers must retain their position in the column after the nth term in the sequence. That does guarantee our repeating subsequence. What do you think?
Very good, isn't it?